Welcome to The Explainer. If you're ready to bypass all the fluff and jump straight into the awe-inspiring science of our cosmic neighborhood, well, you are in exactly the right place. Today, we're taking a mind-bending journey, starting right from the fiery center of our solar system and working our way outward. We're going to explore the ancient worlds and some wild new discoveries that really define our place in the universe. So, let's get into it.
But hey, before we even leave the launch pad, take a look at this. Why is the sun green? I know, it's a completely counterintuitive visual, right? But it actually shifts exactly how we need to look at space exploration imagery. Okay, let's dive into this. You see, our human eyes only pick up visible light, which honestly is just a tiny fraction of what's actually out there. Scientific instruments, on the other hand, are built to detect invisible light, things like extreme ultraviolet wavelengths. And because these invisible forms of light don't have any inherent color that we can see, scientists have computers assign them a false color, like this super bright neon green, just so we can actually observe and analyze the data. This whole concept of the electromagnetic spectrum provides a massive paradigm shift. It really reveals just how narrow our little band of visible light is when you compare it to the massive ranges of short and long wavelengths out there, like X-rays, ultraviolet, and infrared. So throughout this explainer, just keep in mind that the incredible colors we'll be seeing are often scientific tools. They're translations of invisible wavelengths into visible data that let us literally decode the universe.
All right, here is our cosmic flight plan for today. First up, our star, the Sun. Second, space weather and Earth. Third, we'll hit Mercury, the extreme planet. And finally, Venus, the runaway greenhouse. Let's kick things off with Section 1, our star, the Sun, the massive, violent, super hot core engine driving our entire solar system. 1 million. Let that number sink in for a second. That is the mind-boggling scale of our star. You could literally fit 1 million Earths perfectly inside this massive ball of hot plasma. The Sun is just so unimaginably gigantic that it actually accounts for over 99% of the total mass of our entire solar system, the whole shebang. And every single second, right in its core, it's fusing 614 million metric tons of hydrogen into 609 metric tons of helium. And this brilliantly illustrates the hidden forces at work here. On one side, we've got a visible light image of the sun showing these dark, temporary splotches we call sunspots. And right next to it, taken at the exact same time, is a map of the sun's insanely complex magnetic fields, where white is positive and black is negative. If you compare the two, you'll see those sunspots map perfectly onto the intense magnetic fields. It's absolute proof that solar activity is completely driven by these intense, twisting magnetic forces deep within the star. Now check out the scale of this structure captured by NASA's TRACE mission. These are vast, superheated plasma loops, and they're trapped perfectly inside those magnetic field lines above the sun's surface. To really put that into perspective, you could fit about 10 Earths across just a single one of these loops. And the plasma inside, it reaches temperatures of over 1 million degrees Celsius. That completely dwarfs the sun's surface temperature, which is a mere 5,500 degrees. But here's what happens when those twisting magnetic fields break and reconnect. They violently release a tremendous amount of energy. Sometimes a huge prominence, like this massive cloud of plasma held up in the corona, just erupts into what's called a coronal mass ejection, or a CME. It's essentially a huge blast of charged plasma and radiation. And what's really fascinating here is that less than 2% of the sun is made of heavier elements forged in ancient supernova explosions. So when the sun throws a tantrum and ejects this material, it's literally tossing around the very elements that make up you, me, and everything else in our solar system. It's exactly what Carl Sagan famously called star stuff.
Moving on to Section 2, space weather and Earth. Let's head outward from the sun and explore the really dangerous ripple effects its tantrums have on our own fragile planet.
Which brings us right to the concept of space weather. Basically, space weather is the effect that the sun's ejected charged particles have on Earth and the rest of our solar system. You see, the sun's hot atmosphere is continuously expanding out into space, And that creates a constant stream of high-energy particles known as the solar wind. This wind blows out and forms a massive, massive bubble in the interstellar medium called the heliosphere, which is actually the largest continuous structure in our solar system.
Now, what's really interesting about this slide is seeing our planet's ultimate defense mechanism in action. When those massive coronal mass ejections blast outward at like 1,400 kilometers per second, they slam into things in the solar system. But luckily for us, Earth's magnetic field acts as a brilliant invisible shield. It gets distorted into this long oval shape, but it partially protects us from those plasma blasts. Because without this shield, radiation storms could easily trigger massive power outages, severe communications disruptions, and completely knock out our GPS. Obviously, space weather is incredibly impactful to our modern tech-heavy lives. We can't really just cross our fingers and hope for the best. And that's exactly why we use incredible spacecraft like NASA's Solar Dynamics Observatory, or SDO. It's up there constantly monitoring the sun's variability, with the ultimate goal of predicting dangerous solar activity way before it ever hits Earth's shield. Let's move to section 3 and see how this builds. Mercury, the extreme planet. We are traveling to the smallest, closest, and most intensely battered of the inner rocky worlds. If you think Earth has some tough weather, you've got to consider Mercury. It is completely hostile and barren, a true world of brutal extremes. We're talking about the smallest planet in the solar system, the closest one to the sun, with absolutely zero moons, a ridiculously thin exosphere, and the largest daily surface temperature variations of any planet out there. I mean, you go from freezing nights of negative 160 degrees Celsius straight to scorching days of 430 degrees Celsius. It's just an incredibly alien, battered world compared to what we're used to. But here is a truly surprising fact that kind of just upends everything we expect from this baked rock. NASA's Messenger spacecraft mapped these massive impact basins and discovered orange splotches around them that turned out to be volcanic vents. But even crazier than that, despite that blistering 430-degree daytime heat, Messenger actually found hints of water. It's hiding deep in the permanently dark, freezing craters right at Mercury's poles.
No way, right?
All right, section 4. Venus, the runaway greenhouse. Transitioning outward, we hit the second planet from the sun. Now, for decades, science fiction writers dreamed this place was a lush, tropical Earth twin. But science ultimately revealed it to be, well, an absolute nightmare. So the crucial point is understanding the sheer contrast between our inner planets. While Mercury has these dead, airless extremes with a tenuous exosphere and freezing nights, Venus is highly active and completely toxic. Venus has this crushing atmospheric pressure. We're talking nearly 100 times that of Earth. And those thick clouds hiding its surface, yeah, they aren't water. They are literally clouds of concentrated sulfuric acid. It's essentially battery acid raining down. So how did a planet with roughly the same size, mass, and density as Earth go so horribly wrong? Well, about 700 million years ago, Venus experienced tremendous volcanic activity. It completely flooded the surface with lava and pumped the atmosphere full of greenhouse gases. This triggered a massive runaway greenhouse effect. Today, thanks to radar data from missions like NASA's Magellan that peered right through those acid clouds, we know the surface is basically a superheated oven sitting at over 400 degrees Celsius. It's a powerful, cautionary tale of planetary evolution gone terribly wrong. As we start to wrap up this explainer, I want you to consider this map of our 11.8 billion kilometer solar system. Now, it is purposefully not to scale, and here is exactly why. The cosmos is just staggeringly vast. If we wanted to build a scale model of this exact graphic, and we made our massive sun just 1 tiny centimeter wide, we would need about 64 meters of paper just to map the orbits accurately. It is a pretty humbling reminder of our tiny little place out there in the void. Which leaves us with this final thought. We've looked at the violent, millions of degrees plasma of our sun, the freezing to scorching dead rock of Mercury, and the toxic, high-pressure acid bath of Venus. So does exploring these extreme, hostile environments hold the key to protecting our own fragile star stuff right here on Earth? By understanding planetary evolution gone wrong and monitoring space weather that actively threatens our technology, studying the stars might actually be the most vital thing we can do for our own survival. Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll see you next.